Hey everybody. So in this video, we're going to talk about the concept of work. And I'm going to define what that is. This is a concept from physics, not our everyday meaning of work. But I just want to point out that this is not some particularly important example. If you're a physicist, it's super important, but if you're not, it might not be particularly relevant to you. But the point of this is to see an application of kind of some of the methods that we've been using with integrals. This idea of taking when we want to kind of like add up things that are changing, and so we pretend they're constant on intervals and then add up all these little tiny intervals and take limits. So let's get into that. I need to define work before we're able to define work. And again, it's not our everyday meaning of work. So we need to start actually with a concept from physics called force. Okay. And so force is defined as mass times acceleration. Okay, so you may have even seen something like this before, F equals ma. We could also write this as a lot of time. We usually think of mass typically being constant. It doesn't have to be. For most of our applications, it will be. And acceleration, if for instance we have a position function x of t, the acceleration is the second derivative. So this is another way we can write this equation of force. So force is the push on an object, or the pull on an object, right? So you can talk about how hard you're pushing a block, or how gravity is pulling down on you, the force that it's pulling down on you with. And it's a product of your mass times the acceleration. For units, we're just going to use the typical scientific units. Our mass here is in kilograms. X would be in meters. T is seconds. And so this force becomes the mass of kilograms. The second derivative of x would be meters per second squared. And so this is often called the Newton. So these are the units of force in the scientific community. So kilogram meters per second squared is easier. Just think of what we call a Newton. So for example, if you drop a ball, right, the force of gravity is what's pulling it down. That's the force there, gives that mass an acceleration, right? It starts at 0 meters per second when you drop it, and then it starts to increase its speed, which is what an acceleration is. Or if you push a block across a table with some force, right, that's what pushes it. How hard you're pushing it tells you how fast it's going to be moving. In both cases, we get what's called work. And work, in the sense of physics, is defined as force times distance. Right? How much force was applied and for how long? Okay, so we might simplify this as work equals F times D. So for instance, if I were to push let's say push a block with a force of 5 newtons across a counter for 2 meters, then the work I've done would be that force of 5 newtons times the distance of 2 meters, which gives me 10. And looking at the units, this is 10 Newton meters, which we have invented a unit for called the joule. Okay, so that's J-O-U-L-E, I believe. So 10 joules of work. Okay. This is the idea. However, this is a very simple example. And I told you the definition of work is force times distance. This is a little bit of a lie in the sense that this works easily when the force is constant, but that doesn't have to be the case. Okay? What if the force is changing? In other words, what if the force, perhaps as we're pushing that block across the counter, maybe I start out pushing lightly and increase, or maybe as I'm pushing it, I'm growing tired, and so I'm pushing less and less hard, right? So the force might be actually changing. It'd be very difficult to push a block with a force of 5 newtons consistently. And so maybe force isn't a simple number. Maybe force is a function of the position, right? If I'm pushing this block across the table, across some counter, right? Maybe where it starts, I call this x equals 0. And as I move, its position is how many units, how many meters to the right. That's the x value. Well, that force might be changing, right? If this is my x direction, maybe the force starts out very high and then drops as I get closer to the end, right? So maybe if I were to graph it over this, we'd get some kind of force like that. So now I don't have a number that I can multiply by 2 meters because it's changing, right? So the work is actually equal to a function times the distance. But this doesn't really make sense either, because then it's the amount of work is going to be a number at the end, not a function. So here's what we have to do. The idea is very similar to ones we've used before. What I can do is chop up this little interval, right? Let's say, let me make this drawing a little nicer. Let's do this. So let's use that block pushing example. Let's say I'm pushing the block in this direction, and we'll call where it starts 0 and where it finishes 2 meters, right? And all I need to know, I don't know exactly what the function is, but I'll just draw a picture of it. Let's just say that I'm growing tired as we go. So the force is generally just decreasing. Maybe once in a while I get a second wind and push a little harder, but the force is going down as I move across, right? So what I could do is split up this interval. I might call each of these pieces delta x, right? That's the distance of each of these intervals. And I might say, well, on this interval, I could just say the force, which I've sketched in this graph, is this high. I could pretend the force is this strong during the whole interval. I see from my picture it's not, but it doesn't decrease that much over the interval, so it's reasonable to make an approximation with that force. In other words, the work done just on this interval would be whatever my function for the force is, times, let's call this x sub I, times delta x, right? That's the force times the distance. This is the approximation over that interval. But then, of course, I need to do this for each interval and add them all up. And this would give me an approximation for the work done as I push across this counter, right? On each interval, I'm just using one point and pretending like the work done, or the force over the interval is the same, although we can see in each of these cases, in this particular case, I've drawn it so that it's decreasing, right? So it's an approximation, it's not perfect. Also notice, f of xi times delta x is just telling me the area of this rectangle. So it's really the same idea we've been using all along. We're just constructing it or thinking about it a little bit differently, okay? So then we would take the work to be, right? We could get a better approximation if I made these intervals smaller, because then I would get, for instance, here, one rectangle there and one rectangle there. Even though there's still approximation, they're better approximations because there's less interval for the force to change on. So we're closer to the true value at each case. In other words, we let the number of intervals go to infinity. We add up all over those intervals. And we end up with an integral. So I've drawn it from 0 to 2. Let's just make it general. Whatever length we're integrating over, the function, the force function dx, right? And so if we know this force function, we can integrate to get the work over the whole thing. Okay. So let's do an example of this where we can find this work function. So this is a pretty classic example. It's going to use something called Hooke's law. Okay, and this has to do with springs. So let's just write Hooke's laws. This is the force, and then I'll explain exactly what I mean. The force to maintain a spring stretched X units beyond its natural length. Oops. Is given by f of x equals kx. All right, I'm going to explain all this in a second, but let's just say where k is greater than 0. Okay, so let's go through a few things. Let's first draw a picture of what I'm trying to say here. So let's say I'm just drawing a little wall with a tabletop next to it, and let's suppose I have a spring attached to this wall. All right, there's my little spring. It's got a little knob on the end that I can pull. So a spring is going, oh, let's give it something to sit on the table. It looks a little weird. So it's attached to some kind of block that sits on the table, right? And so depending on the setup, right, that spring is going to want to be somewhere, right? If you push it in, it's going to want to push back out. If you pull it out, it's going to want to push back in. So where it would sit naturally without anything acting upon it, we call that its natural length, and we're going to give it an x value of 0, right? Now, suppose I were to take this spring and stretch it, right? So now I've moved it from its natural resting spot. Oops, I didn't mean to change that to green. Let's use green. We've moved it some distance. We're calling x. How far beyond, right? So depending on how far we pull it, notice what happens. K is positive. We'll talk about K in a second, but for now, just think of it as it is a constant. It's a positive constant. So as I stretch it, the force goes up, and we can all probably imagine this. You take a spring, when you pull in the beginning, it's not that hard. The further out you get, the harder it gets, okay? Generally. I should mention Hooke's law breaks down eventually. If we pull too far, you may have done this where you kind of break a spring where it doesn't pull back anymore. But for small enough values of x in its kind of range where it works as a spring, Hooke's law works out. Okay, so it matches with intuition. As we pull it further, it becomes harder and harder to maintain it at that distance, right? If you've ever worked with like an industrial spring, like shocks or something like that, it's almost impossible to pull it all, and you have to apply a ton of force, right? K just depends on the structure of the spring. What's it made out of? How tight is it coiled? How big is it? All these kinds of things that engineers would know a lot about for figuring out. And so that's something you would know from experiment, okay? So that's the idea. At each point, at each position here, there's a different amount of force required to hold the spring in that position. So here's the problem we want to solve, okay? Suppose we have a spring. It takes 50 newtons of force to keep the spring 20 centimeters from the natural position. Okay, that's our first fact. Oh, excuse me. That's not. Let me restate this problem. I want to use the problem as I wrote it. To keep the spring with a natural position of 20 centimeters stretched to 30 centimeters. Okay, so its natural position is 20 centimeters, and we're stretching it to 30 centimeters. Okay. And then the question is, how much work is done to stretch the same spring from 20 centimeters, its natural position, to 35 centimeters. Okay, so there's our question. Okay, so let's draw a picture. Just draw another picture. Oops, I want this. All right, so here's our little diagram. My spring, I'll draw it in red again. It's resting on something out there. So this position right here, which is 20 centimeters out from the wall, but what we're calling it, let's insert a little number line. So we're calling that position here 0. Okay, so our X doesn't represent how far it's from the wall. Remember, X represents how far it is from the natural position. Okay, and what we learn in the first case is that when we move out to 30 centimeters, we require 50 newtons of force to keep it there. But remember, that's just going to be 10 centimeters past the natural position. Okay, so what that information is good for here is to get Hooke's law. Let's think where we're going, because later we want to figure out, we want to now imagine stretching the string from, let's move this, well, it doesn't matter, from 20 centimeters out to 35 centimeters, or from 10 centimeters past to, sorry, from 0 centimeters out to 15 centimeters past the natural position. We want to figure out how much work that's going to take. We're going to have to add up all the little pieces of force times those little delta x's in the example above when we develop that integral formula for work, right? However, we don't know f of x. Let's just go up and look for a second. Remember this formula here, we're going to take our force function and integrate it over the interval that we care about, but we don't know the force function yet because we need to know what k is. But we have information here to understand k. In other words, we know the f of x equals kx. And what this first sentence tells us is that the force of 50 newtons is required at a distance of 20 centimeters, which is going to be, sorry, not 20, at 30 centimeters, which is 10 centimeters past natural. But we've got to be careful. We need our units to work out because newtons is in meters. So let's change everything to meters. This means k times 0.1 centimeters. In other words, we get 50 newtons divided by 0.1 centimeters equals k, or 500 newtons per centimeter is equal to k. Okay, that gives us the value of k. That tells us something about the strength of this string, right? If you were at, sorry, not centimeters, meters. I just changed it to meters to make this work out correctly. Okay, newtons per meter, right? In other words, if you were to hold this, pull this spring out to 1 meter, you would have to use 500 newtons of force to hold it there. Okay, and if you could pull it out 2 meters, you'd have to use 1,000 newtons, right? It may break at that point. Like I said, it's only valid for certain values of position, but we're in this problem, we're assuming we're staying within that range. Okay, so now what we have is a function. Our force function is 500. Let's throw units in there. 500 Newton meters times x, which x is our position, so that's going to be in meters. Notice we'll end up with newtons, which is exactly what force is. okay? All right, so I'm going to simplify it and just write 500x. We know our units check out, so I'm going to simplify how it looks for now. And now we're just using the work formula. Work is equal to the integral from 0. We're going out to 15 centimeters, 0.15 meters. Our force function dx, right? Now, behind this integral, remember what we've done. We're pretending that we start by dividing the interval from 0 to 0.15 meters into little intervals, and we pretend the force is constant over those intervals, and we're using our force function 500x. And so over the first little bit of this, we take 500 times whatever this position is times that little delta x, and then add it to the next position times delta x, and so on and so forth. And then we take a limit and shrink those intervals, and we get this integral. And then this integral is pretty straightforward to take. The antiderivative of 500x is 250x squared. We're evaluating it from 0 to 0.15. So we get 250 times 0.15 squared minus 0. I'll just write it, 250 times 0 squared. And this works out to be 5.625 joules. Okay, and that's it. That is our idea of work, right? The point again of this is to just show you that we can take this idea of something that's constantly changing, and we take little pieces of it and pretend it's constant in order to do what we want to do. And then in the limit, everything works out, right? So it's a pretty nice strategy that can be applied over and over again. Okay, thanks everybody. I will see you next time.